Okay, so in this video, we'll try to understand the concept of entropy, and basically, it will be kind of introduction to entropy. So, entropy, actually, if I write down, let's say, entropy. So, this is the word, one of the most confusing word in thermodynamics. It's kind of abstract term, really hard to understand, really hard to put a definition. Like energy, we know the term energy. So energy is the term. It's we could not define energy, clearly, but we know energy principle and the energy, energy conservation principles. Yeah. So if I ask you, okay, what's the definition of the energy? So it's sometimes really hard for us. So entropy is some kind of concept, some terms, but this is the first time we're just trying to understand this concept. So definitely, when we will go through more contents, more the statements, then when we will introduce ourselves with more practical application, then it will be clear and our knowledge will increase. So in general term, entropy said it is actually the amount of disorder in a system. So if I write down here, we said the entropy is amount of disorder, okay, in a system. So you can say this term disorder, or you can say randomness, okay, you can say it is the randomness. So entropy, we said it is the amount of disorder in a system. If we just extend this definition, then we can say the amount of disorder of molecules in a system, or randomness of the molecules in a system. We'll try to understand that. Look, these two images here. This is a room. It looks very worded, and you can see this room. It looks messy. So if we try to correlate these two pictures with this definition here, it says amount of disorder in the system is entropy. So we can see it is less, this room, it is actually less messy, and it is definitely messy room, right? So what we can say, the entropy of this room is lower than this room, right? The entropy will be higher according to the definition. So the term disorder, it's not like that. It's so what it is. Then if it is not, so we can tell that okay, the entropy in this room will be higher than this room. So it's not like that. And I said the term disorder is not that way, not that sense. So then what's the actual meaning? This disorder actually tells the number of states, a randomness of this of a system. So if we consider this is a system, look at this example here, guys. If we consider this is the system, this is a molecular system. We have the molecules here, different colors molecule. You can see the red and the other color. So at first state, let's say it is here. So molecules inside the system, they can continuously move. They can randomly, travel here and there. So let's say after 1 second, we found the molecule is here. The red one, we are looking for this specific red molecules. When it is a state 3, it changes the states. At a state 4, it changes the states. So it could be this system, we can get a lot of possible combinations where this molecule can, travel. So they are just these molecules, you can see they're continuously moving. I didn't change the other molecules a lot, but I'm just trying to focus on this red molecule. So what we can conclude from here is, in a state, in a system, these molecules, they can travel a lot of places, so a lot of states we can get from here. So this change of the state, the positions with time, we are trying to say this is actually the state. Okay, so then what's actually, then how we will correlate this with the entropy. So we said entropy is the disorderness or the randomness of the molecules. So if we can see, okay, if we have this system and if we have another system, let's say a large system, so that means we have more molecules. We have a lot of molecules here. So then we will get more randomness. Then so for this system we will get more disorder or randomness or more states than these molecules, these systems. Okay, so what I'm trying to tell you is more disorderness or more states means more entropy. More entropy. So let's go to the another example, and then it will be clear that how entropy increases. So when it is solid, so molecules are very close to each other. They have the van der Waals, attractions, the intermolecular attractions. So they are very close. They are very ordered. So now when this solid change to the liquid phase, then the bond between the molecules, destroy, and they are not anymore in the organized position. So now they are random. So if the entropy here, let's say S1, entropy here S2, it is S3. So then we can say clearly it is more ordered than this state. So the entropy for S2, it is greater than S1 because it's more random. When it is gas, then it is very spontaneous, kind of Brownian motion here at this state. So S3 again, here we can say S3 is greater than S2, greater than S1. So you see the increase of the entropy, it increases with the randomness of the molecules. So more random, more disorder means more, entropy. So now what's the relations? We found, okay, this is the randomness of the molecules or the randomness of the system is entropy, and more random means more entropy. So then how we will correlate this with the temperature? We are familiar with different the property diagram and the phase change tables. So let's say if we have if we have this, let's say this is T and this is S. S is the the entropy, T is the temperature. And if we have a process like this, so what we are trying to say, this is process 1 or state 1, this is the state 2. So we know if we go this way, temperature will increase, the entropy will increase this way. So here we can say, here let's say this is temperature T1. At this position we can say this is temperature T2, and if we come this way, then we can say this is entropy S1, this is S2, right? Yes, I believe you understand. So if we try to correlate this with a piston cylinder device, let's say we have the piston cylinder, this is our piston, okay, and we have put some molecules here. So this, what it means, this process curve from process 1 to 2, it means the temperature here, it was T1, it is higher than T2. That means the temperature is decreasing, and it means actually this system will expand, this gas will expand. If it expand, then let's say the piston will go to this position, let's say just for demonstration purpose. So if the gas expand, then temperature will decrease, and temperature decrease means, guys, look here, temperature decrease means, so let's say the piston will go this position, so the volume will increase, so it will get more space. So initially all the molecules was here, and now it will get more space. That means we will get more randomness of the molecules for expansion process, right? So what we can say, the temperature decreased means the volume will increase and the randomness will increase. So you see here, when the temperature is higher, that means less randomness, less entropy. When the temperature decreased, the volume increased, and you can see the entropy increased. So you can clearly correlate here, guys. The low temperature means when the temperature is higher, the entropy is lower. When the temperature is lower, entropy is higher. So entropy, we can say the entropy as it is actually function of temperature. And high temperature means high temperature means the low entropy. Low temperature means high entropy. So we define entropy by S. In the upcoming videos, we'll try to understand this expression, these relations. Will definitely solve some more problem, and then it will make it clear to you actually the relations between the temperature and the entropy. So I believe you understand actually the entropy definition, like the randomness will increase. It means here actually for this piston cylinder device the volume increase, it will get more space, so that means it can expand, expand here and there, the kind of Brownian motion of the gas molecule will increase, so it will definitely increase the entropy. So I believe you understand, and I uploaded some more videos for general understanding. You will get it from UTS Online. So that's it, and I will discuss it during my lecture.